Anyway, today we're very lucky, fortunate to have Mark Blyth from UEA. He gave me his full biography, but I'll cut to the important bits. He was an Imperial, PhD Jonathan Mestel, worked with Phil Hall, and spent some time in San Diego, in fact, although I didn't know him then, I just saw him once. He's been at UEA for a while, and he's spending some time with us to talk about a model of a deformable aerofoil.
Yuri, thanks. Thank you very much, Stefan. Am I supposed to be doing something with the recording?
You just talk.
No, you're on there.
You're on air.
Okay, well, thank you very much for the invitation to speak. So this is my title, Towards a Model of a Deformable Aerofoil. A lot of what I'm going to talk is not going to look like an aerofoil at all. Actually, I'll explain what the problem is going to be, but it will become a little bit more realistic in that sense towards the end of the talk. Okay, so if you're thinking what this is, so I'm going to show examples of shapes that are in no sense an aerofoil, and very obviously so. Okay, change towards the end of the talk. So I'm from UEA in Norwich. Norwich, if you're not sure where that is, it's about an hour on the train northeast of here. Very importantly, I should say this is joint work with Adam Yorkston, who's a PhD student at UEA, so he did all the work, and then my colleague Emilian Perau, we were his supervisors. So the motivation, or actually, if I'm completely honest, this is not the motivation. If I'm completely honest, we started looking at this problem because we thought it was fun. And then we started trying to think of how it might be applied to something. And this is what we came up with. There's been quite a lot of interest in thinking about aerofoil shapes that have some ability to deform in response to the flow and the aerodynamic forces upon them. I guess with a view to improving aerodynamic efficiency, that sort of thing. Taking inspiration from nature, here's a picture of a dragonfly. The wings are flexible to some extent, so they're not rigid. They can deform under flow. And similarly with birds and feathers and so on. And engineers have taken inspiration from this and created some examples. Here's a picture of what's called an unmanned aerial vehicle. There's no obvious scale here, but this is very small. So it's sort of on the order of a metre large, something like that. And the wings, you can see the yellow things, are inflatable. And as far as I can tell in this example, the idea is they're inflatable for reasons of portability. So when you finish flying it, you want to be able to wrap it up, which is what's happening in the picture above, and then carry it away easily. There's a nice review article I found on endeavours with deformable aerofoils, going all the way back to the Wright brothers as to what people have done to think about this. So in many cases, the idea is just to make part of an aerofoil deformable, so some component like the trailing edge, for example. What we're interested in is the whole thing is able to deform in response to flow, like this inflatable example. Okay, so here's the actual problem I'm going to talk about for a lot of the talk. It's, take here, this central bit here is an elastic cell, which means it's a constant pressure region. So inside, so these are streamlines. Okay? This is a uniform stream going past an object, this kind of elliptical shape looking object, whose boundary is elastic. It's a very thin-walled elastic cell, so it develops elastic tensions and can withstand tension and pressure differences, and so therefore can deform in response to the flow around it. And the region inside is just constant pressure. So it's like a bubble, but the wall has not got a constant surface tension. It can develop elastic shear and out-of-plane tensions, as I'll explain in a minute. And the question is, if you put this thing in a uniform stream, what shapes does it deform into? So there are really two effects here. One effect is...
May I ask you about what do you mean elastic? It's a shell, it is a membrane, or
so
it is a linear elasticity?
So I need to be careful with this because it can support bending moments. So that means it's a shell or a membrane. I always forget which way around it should be. It's a shell. Okay, so there's going to be bending moments. So there's going to be two effects for the deformation here. The first one is that there might be a pressure difference between the pressure at infinity state and the pressure in the interior. So we'll set that as a parameter. And the second is the effect of the flow. Okay, so the flow, as the fluid goes past by balloons, everything I'm going to talk about is inviscid, by the way, as well. And almost all of it is inviscid in irritation. So also, according to Bernoulli's equation, there's a pressure variation around this cell. If you get rid of the flow and just look at a completely static cell with a difference in pressure between the interior and the exterior, that's a fairly classical problem that's been looked at by a number of authors, which I'll come to in a second. But before that, let's draw an analogy with a bubble, because there are some analogies to be drawn here, and some of the techniques I'm going to use are very much inspired by the work on bubbles, particularly Sally's work here, Nian Tanvir and Tanvir in 1996. So thinking about a 2D bubble, here's a brief summary of some of the most important works. And Shankar and Tanvir is complex variables. I think Van der Broek and Keller is boundary integral calculations. And Nian Tanvir is complex variables as well. And I'm going to be using conformal mappings to do this, incidentally, in keeping with the program. So here's the static problem. So no flow at all, just a cell exposed to what's called a transmural pressure. So the pressure difference across the wall is non-zero. And this problem goes back a long way to Levy in 1884. Probably the easiest reference to look at on this problem is the one by Flaherty, and Joe Keller is one of the co-authors in 1972. And if you start with a cell that's perfectly circular, I'll show you this in a little while, and then you increase the pressure so that the pressure outside is larger than inside. Eventually, as you ramp that pressure difference up, you'd expect that it's going to buckle, and that's what happens. And it can buckle into shapes with different degrees of rotational symmetry. I'll show you some examples later. So our interest really was to take those buckled states and ask what happens if you put them into a flow. So let's develop the equations we need to use. So imagine a small segment of this elastic cell of length ds. So S is going to be arc length around the boundary. And to all intents and purposes, the thickness of the shell is 0. Okay. Then there's an in-plane tension, that's capital T, an out-of-plane tension, capital N, and a bending moment, capital M. And there's a pressure force acting on the cell boundary, which in general depends on S if there's a flow. So if it's the Flaherty problem, it doesn't depend on S, it's just a constant. But according to Bernoulli's equation, if there's a flow, it's going to vary along the boundary with respect to arc length. And the cell might have some weight as well. Okay, so if we're thinking about the problem that I motivated this from, then presumably the thing has actually got some weight. And if you don't do anything, it's going to fall to the ground. So let's do a balance of forces on this segment, assuming that it's in equilibrium. Okay, so it's not accelerating. Across this small segment of length 2 ds. So these are the forces at the ends. The capital N, little n hat is the normal, and tau hat is in the tangent direction to in the direction of increasing arc length. Hopefully that's obvious from the picture. And then that's just the load on the cell, the second integral from the pressure and the weight. And that's got to equal to 0 if this is an equilibrium balance.
Sorry, Mark, we're not worrying about anything inside the cell. There's no gas or anything like that.
There is a gas, but it's just a constant pressure. So it's
Integrates out.
It's very simple. Right, take the limit as ds goes to 0 and you'll get this equation here. And then we're going to differentiate this bracket. When you do that, you'll have to differentiate the unit vectors n hat and tau hat, and that will introduce curvature. So that's what happens on the next slide. So for example, I can define my curvature as n hat dot d tau hat by ds as a measure of how tau hat is changing with s. So that equation there is the one from the previous slide with that differentiation expanded out. And also I've written j, so I didn't say j is the unit vector up the board, so the direction, the negative direction of gravity. I'll rewrite j in terms of n hat and tau hat, and that introduces dx by ds and dy by ds, where x and y are just a point in the cell wall that depends on s. Okay? And there's going to be 2 rows in this talk, so be a little bit careful. Row C here with the subscript C is the density of the cell wall, as opposed to the density of the air on the outside. Okay, so that's just an equilibrium balance of forces. Do something similar for the moments. Look at the balance of moments. We've got the moments and the ends on the left-hand side of that equation, and then the moment generated by the out-of-plane force, capital N, on either side. Take the limit as ds goes to 0, and you get that result, that n is dm by ds. This is all pretty standard stuff so far. So this is in Flaherty's paper, for example. Then you'll need to make some assumption about how the curving of the cell relates to the bending moment. And a common choice for this, which can be justified in the case of an inextensible cell, which incidentally is what I'm going to assume. So the elastic material making the cell up is not extensible in everything that I'm going to talk about. So this can be justified for an inextensible cell, that the bending moment is basically proportional to the curvature. So this is assuming that the rest curvature of this thing, in other words, the the curvature of the state it wants to assume in the absence of any loading. That's assuming that's a constant. So the thing is either flat in the rest state or a circle. Okay. So here's a summary of those equations. There's a balance of tangential force, a balance of normal force, and the moment balance. If I put in my constitutive equation into here and then substitute that into the first equation at the top, what we'll get looks like this. So the tangential balance now, you can see you can integrate once with respect to s. Okay, so every term there we can integrate with respect to s, so we can do that. When you do that, you'll get a constant of integration, which I'm going to call sigma, and this thing sigma is going to hover around for the rest of the talk. It's this constant of integration, which ultimately is going to be fixed by requiring that the cell is inextensible and closes up, so the thing is periodic in S. Okay, so those are my two equations so far. Now I can take that equation for capital T, the first one, substitute it into the second one, and I'll get an equation for the curvature like this. That's those equations combined. And if you knock out the weight, so you just get rid of gravity, so get rid of the first term after the equal sign, and you assume that little p is a constant, that's the equation in Flaherty's paper for a static cell. So let's think about that case to start with. So take p to be a constant and get rid of gravity. What do the solutions look like? Okay, sorry, we'll get to that in a second. Let's just talk about the formulation in the presence of flow first. So I want to take a conformal mapping approach to this. So I'm going to define a velocity potential W, such that in the normal way, the W by dz is u minus iv. U is the velocity in the x direction, v in the y direction as normal. At infinity, so these arrows are not really drawn as though they look as though they're at infinity, but capital U is supposed to be the flow speed coming from the left at infinity, and P infinity is the corresponding pressure, and P0 is the constant pressure inside the cell. So there's my transmural pressure, P infinity minus P0. Little q henceforth is going to be the flow speed, so that's just the modulus of W by dz. I've got a kinematic condition to satisfy on the cell boundary whose shape is unknown. Okay, in advance, so it's a free boundary problem I'm trying to address. Let's let eta represent the position vector of a point in the cell wall, so that's just my kinematic condition saying that a point on the cell wall moves with the component, the normal component of velocity local to it. We can write this in terms of complex variables, so now there's a slight shift of notation. Instead of eta being a vector, I'm going to represent it as a complex number whose real part is x and whose imaginary part is y. Okay, then I can rewrite my kinematic condition like this instead of the one from the previous slide. Okay, it's equivalent to that dot product, or those two dot products on either side of the previous slide. And phi here is just some parameter that parametrizes the boundary. Now the setup in the far field, because I'm interested in aerofoils, I want to allow this thing to have some lift on it. So I'm going to take the flow in the far field to be a uniform stream, so capital U times Z, and to have some circulation in the normal format, so capital gamma times log Z. And capital gamma, I'm going to be careful to take to be real, because I want to conserve area inside my cell. So I'm going to not only conserve the perimeter of the cell, I'm going to demand that the area inside the cell is conserved as well. Okay? Now that's equivalent to saying that there's no points, that's equivalent to saying that there's no change of mass at infinity. This thing's not acting as a point source or sink if you look at it a long way away, and therefore gamma's got to be real. Okay? That same point, if that's not clear, is made on this slide. Okay, so there's my flow at infinity. If I write down a formula for the area of the cell, it's just a geometric formula for the area capital A inside the cell, then it's straightforward to show. Now it's relatively straightforward. If we differentiate this with respect to t, then that derivative, taking the d by dt inside the interval, can be translated into this. And then if you play around a little bit and use the kinematic condition, you can show that's equal to 0. Okay? So I'm going to conserve the perimeter of the cell, because I'm going to say it's inextensible, and the area inside. So the problem is now set up naturally to do that. There's going to be three parameters, three dimensionless parameters if we non-dimensionalize. Little l here on this slide is the perimeter of the cell. EB is the bending modulus that appeared in that constitutive relation between the moment and the curvature. Capital U is the flow at infinity, and rho now is the density of the air. Okay? So the fluid, or it doesn't have to be air, but the fluid outside the cell and inside it. So that's another point I should make. There's gravity here, but the density of the medium outside the cell is assumed to be the same as inside, so there's no buoyancy. Well, there's effectively no buoyancy because the cell wall is so thin. And the pressure parameter is effectively the transmural pressure, the difference between the pressure at infinity and zero, which I guess in a regular aerofoil is likely to be zero or close to zero. And beta is encapsulating the effect of circulation, so lift. So we address this with a conformal mapping approach. This is exactly the way that Shankar and Salo did this for the bubble problem. I'm going to take my elastic cell shape that I don't know and map it onto a circle in the zeta plane. And with mapping the exterior, so the z plane is the physical plane where the problem is defined, I'm going to map the exterior of the cell to the exterior of the unit circle. So by Riemann's mapping theorem, I can do that in this way, by fixing the point at infinity and by demanding that a minus 1, a subscript minus 1 is real. So Riemann's mapping theorem tells me if I do that, if I map infinity to infinity and I take that coefficient to be real, then the mapping is unique. And all that remains to be done is to work out these coefficients an, which are in general complex, and that one which is real. This is a completely general mapping taking me from a smooth shape in the z-plane to the zeta plane. And of course the reason for doing this is that in the zeta plane I can write down the solution to my problem straight away. It's just a uniform stream past a circle. So the complex potential, which is capital W in the mapped plane, takes that form.
Do you have a log as well?
Oh, sorry, yes. So yeah, there should be a log here if we have this. I've left that. Okay, so that's kind of standard stuff. So now what's the problem we've got to look at? Okay, we start by thinking, so most of what I'm going to talk about as well, I'm interested in equilibrium states, where the flow is steady and the cell is not changing shape in time. In which case, I should have a balance on the boundary of the cell between the elastic forces and the pressure imposed by Bernoulli's equation in response to the flow. And that's what that equation is. So what I've done is taken the equation that I derived before and replaced p, little p, as a function of s, with what you get from Bernoulli's equation, fixing the Bernoulli constant at infinity in the usual way. And I've also non-dimensionalized. So that's the dynamic boundary condition on the cell wall, balancing the effect of the pressure force against the elastic forces.
So which one is the velocity squared term?
That's q. Q is the speed, so that's q squared. The other thing to say about this is that these parameters alpha and beta, if you remember, depended on rho, the density of the air. So in that equation, there was no rho c anymore. That was the density of the cell wall. So implicit in writing that down, I've eliminated rho c through this equation, which says that the lift on the cell exactly balances the weight. Okay? Otherwise, I can't have an equilibrium shape because it would be accelerating. Okay? So lift balances weight, and that effectively eliminates rho c, and then I can look for equilibrium states. Okay, so that's the dynamic boundary condition. Kinematic condition, the one we had before. Now everything is steady. Okay, so I want to look for a steady shape. Phi now I can think of the point on the unit circle in the zeta plane, and I'm going to demand that the cell is inextensible, which is encapsulating this integral constraint at the bottom. And eta, to remind you, is just the shape of the cell, which we don't know yet. Okay, well, I'll start by talking about states with no circulation. Okay, so forget circulation, we'll set that to 0. So there's now no lift, and there's no mass of the cell either, so we're getting rid of gravity too, just for simplicity to begin with. Right, so now let's discuss what happens if the thing is static. So alpha, the parameter alpha is basically the flow speed. If I set that to 0, there's no flow, and it's the static case looked at by Flaherty et al. In 1972. The key parameter now is the transmural pressure, the difference between the pressure outside and inside. And it turns out that as you ramp that pressure up, this is what I was describing before, you go through a sequence of bifurcation points which have a very nice simple formula. They're just n squared minus 1, where n is an integer. As you go through each of those values of n, a circular cell wants to buckle into a shape with n-fold rotational symmetry. So when n is 2, it wants to buckle into a state with 2-fold rotational symmetry, and so on. And furthermore, after the buckling has occurred, if you keep increasing the pressure, then the cell wants to pinch together and eventually touch. Rather than me trying to gesticulate to illustrate that, let's show you some pictures. So if delta P is less than 3, so the first buckling pressure went into 2, delta P is equal to 3. Everything just looks circular. Then if we increase delta P above 3, we buckle into a shape of two-fold rotational symmetry like that. And you keep going, you'll get to a critical value of delta P, which is found numerically, incidentally, to be about 5.247, where the cell touches itself in the middle, and you can keep going. Okay, you can push delta P higher, and you'll just get shapes that self-intersect, which don't have any obvious physical.
Mark, quick question, does it mean that the symmetric solution does not exist anymore, or is just unstable?
No, it's still there, it's unstable. Yeah.
It's still there.
Yeah, it's still there, yeah. So delta P, push it above 14. That should say 15, probably, should it? Oh no, was this 4 squared minus 1? It should probably say
3 squared minus 1.
3 squared minus 1.
That's 8, so
Oh, so that's fine. Okay, thank you. Oh yes, the 8. Okay. So you get mode 3-fold rotational symmetry modes, and so on. So at this point, the mode 2 shapes still they coexist with these, and so does the original circle, and so on. Those increase delta P to a critical value, then you develop points of self-contact, and with mode 4 shapes, it's similar. And again, you can extend the calculations, and the shapes will self-intersect. The particular feature of Flaherty's paper, incidentally, is that they extended the solution beyond this point, allowing for a line of contact. So you increase delta P, and this point of contact extends out into a line with a local similarity solution describing that step. Okay, so you can always do that if you wish. Right, now let's introduce some flow, and we'll start thinking about this in the context of weak flow. So let's let alpha be small, and again, ditch circulation, so beta is 0. There's the dynamic boundary condition again, with those assumptions. Well, if alpha is small, we might try expanding in powers of alpha, and the obvious power of alpha, given the form of the dynamic boundary condition, is alpha squared. So that's what I've done here. The leading order solution here, k is -1, is a circle, which is defined to have negative curvature. The flow speed, -2 sine s, that's the slip velocity over the surface of a circle in a uniform stream. So that just comes from Bachelor's book, for example. And then plus some perturbation that we'd like to find. And sigma is this constant of integration. Okay, so we have to play with that as well, expanding in a similar way. Substitute these in. At leading order, nothing particularly interesting happens. We just get a relation between capital P, that's the transmural pressure, and sigma naught. It's at first order alpha squared, that the interesting thing happens. So we get this equation for the perturbation to the curvature. So this is the deformation from a circle under a weak flow. Capital P is the transmural pressure which we can choose. That's a parameter. Now, what stands out from this equation is if I choose capital P to be 3, then I'm going to get a resonance in that equation. And I'll get a complementary function cos 2s, which is going to resonate with the right-hand side. But I must have a periodic solution, because my cell's got to close up. So that's not okay. So any other value of P, it seems to be all right. I can just solve it, and I can look for a periodic solution. But at that value of P, you've got to be careful. And that value of P corresponds to the first buckling pressure of Flaherty et al.'s work. Okay. Well, if I want a periodic solution, okay, I've also got to be careful with the value of P. That's got to be the square of an integer. But if little n is 2, then it seems to be problematic. And it works for any value of n except 2. It turns out that at n equals 2, you've got to revisit the expansion. And instead of expanding in powers of alpha squared, you expand in fractional powers, alpha to the 2/3. Let me just try and explain why you might do that. The problem is the cos 2s on the right-hand side that's resonating with the complementary function on the left-hand side. So you've got to try and get rid of that complement. You've got to try and get rid of that cos 2s on the right-hand side. So I've put in this little aid memoir here of this identity, which I'm sure everybody remembers. But if you take cos and you cube it, then you generate the cos again. Okay, the cos 6s bit I don't care about, but if I take cos 2s and cube it, I get cos 2s again. So that suggests, if I expand in powers of alpha to the 2/3, At first order, the K1, it doesn't see the right-hand side, the cos 2s, because that's too small. Okay? So at leading order K1, I'm just going to get a homogeneous equation with the same operator as before. I get this equation is 0 on the right-hand side, and one solution is K1 is cos s, and another one is K1 is cos 2s and sine 2s. Then if I go to third order up to here, the third order equation is going to see that K1 cubed, because there's a K cubed in the equation. So the cos 2s from the K1 solution is going to get cubed. That will generate a cos 2s term, and then if I play with my coefficients correctly, I can use that to knock out the right-hand side and remove that resonance. So that's the idea. So just to show you very briefly the details, so there's the first order problem. That's what I was describing a minute ago, with arbitrary coefficients that I can choose. If you then go up to third order, skipping all the details, I can choose little a1 and b1 to knock out that cos 2s on the right-hand side of third order. Okay? And get a periodic solution in that way. So this is how it works at p equals 2. You have to expand in fractional powers, and that suggests that something interesting is happening in the bifurcation structure, incidentally, at this value of p, as you might expect on the basis of Flaherty's calculations. So just to illustrate that, what I'm showing here is, so on there's three separate diagrams here. On the x-axis of each is alpha. Ignore the hat, please. That's just the flow speed. And alpha positive is the only thing relevant for our problem. I've shown alpha negative as dashed lines, just so you can see the structure of what's going on a little bit more nicely. And the vertical axis is just some measure of the solution. In fact, it's the integral of the curvature squared around the boundary, like a measure of the bending energy. When p is just above 3, that's this one, that's the solution structure. As p gets closer and closer to 3, this hoop, or this loop, shrinks down to a point, and we get a cusp exactly at p equals 3. Okay? And this is why the expansion changes from a regular expansion in powers of alpha squared to 1 in powers of alpha to the 2/3. That's where that cusp comes from. And the blue circles on there, incidentally, are that asymptotic approximation. But exactly p equals 3, so it seems to work very nicely. Okay, well, the downside of that, the way I've presented that analysis to you, is that it's not just to skip back slightly, it's not obvious how you extend that to higher order. Okay? The argument I just gave you only required information about the leading order flow, which sees a circular boundary, and that's easy to solve. Going up to next order, that sees the perturbed boundary. It's not obvious how you proceed. The nice thing about the conformal mapping approach is it's entirely obvious how you proceed. So here's the conformal mapping I gave you before, no circulation. We can now just, the unknowns of these coefficients in the mapping, I can, if I want, expand the coefficients in powers of alpha squared, except when p is 3, be careful, and just carry on. And you can just go through churning around whatever order you like and work this out to arbitrary order. What you find, incidentally, is that all of those Flaherty pressures, all those capital P's, you have to think more carefully about your expansion. But the most dramatic one is the resonant one at p equals 3, where you have to introduce fractional powers. All the other P's, the powers are still regular, but you have to be a little bit careful with how you do it. Okay, so we'll skip all the details. Let me show you some of the results. So here are some cells in flow. And what I'm showing you here is, so alpha is 1, okay, and these are the cell shapes with streamlines around them, fairly obviously. The left-hand side is p equals 2, that's below p equals 3, so these values of p have been chosen to be above and below 3. And notice what happens. Below 3, the equilibrium shape you get is, if alpha is very small, it's very close to an ellipse. And as alpha gets slightly bigger, so by 1, it's kind of like a slightly rounded ellipse. But it's got its major axis vertical, so orthogonal to the oncoming flow. When p is above 3, same value of alpha, it's the same deal, but now it's a rounded ellipse with its major axis aligned with the flow. So it matters critically whether you're below or above 3 as to how this cell responds, the equilibrium state responds to the flow that's being imposed upon it. Okay, well, just like in Flaherty, we can get shapes with different degrees of rotational symmetry. And here are one's mode 3 type shapes. So I've just chosen a value of p above the Flaherty critical pressure. Well, okay, the Flaherty critical pressure doesn't apply directly here because alpha is non-zero, but it's roughly 8 as before. And I think the thing that's perhaps surprising here is that you can get a steady solution which is not top-down symmetric. That's the one on the right-hand That was a surprise to us when we found that. It didn't seem to be intuitively clear that that would be possible. Nonetheless, there it is. And here's a sketch of the bifurcation structure. The solid lines, and so that's capital P along the x-axis, the bending energy, that's the integral of the curvature squared around the boundary. It's a convenient measure for, almost the curvature squared at the top. The solid lines here correspond to Flaherty's solution, the static cells. And those are the bifurcation pressures, 3, 8, 15, and so on. And the broken lines are what you get when there's flow at alpha equals 2 in this case. Okay? So, for example, on this branch here, if I choose P above 3, then I've got 2 mode 2 shapes there corresponding to. So that branch there is the one that, let me see if I get this right, has its major axis aligned orthogonal to the flow. This branch here was aligned parallel with the flow. Okay? And this branch here, so I guess a point of interest here is that bifurcation point at 8 has moved out to bifurcate non-linearly from this broken branch. And those are the 2 mode 3 shapes coming off there. The one that was top-down symmetric and the one that's not top-down symmetric.
Which ones are stable here? Or you don't know?
So, okay. So the answer to that question is complicated. I'll give a partial answer in a bit, if it's okay. In fact, so here we are. If we want to address the issue of stability, then there are 2 ways we can do this. One is by trying to compute eigenvalues for normal modes, which we did. I won't give any detail, but we did that. And the other is to solve it as an initial value problem. By integrating the full unsteady system, which I've not written down, but if we put all the time derivatives back into the problem, we can integrate forwards in time, and as I said, watch the evolution of a cell from some given initial state. So let me show you if this movie is going to work. Let me start this. What this movie is showing is a cell which is a mode 2 shape. Okay, so quite a deformed shape for some value of p, which I can't remember, and it's seeded at t equals 0, so it's unstable, incidentally. Okay, so the linear stability calculation shows this is unstable. There is one unstable eigenvalue, and this calculation is seeded with the eigenvector corresponding to the unstable eigenvector. This is what we see. There's no circulation; it's just a uniform stream coming towards it. Quite a long period of time, it appears not to be moving, and then it suddenly flips over, and the whole thing moves downstream slightly. If you watch the x-axis, you can see that it's changing. And this kind of motion repeats. So it looks like the static equilibrium shape for a while, and then it flips over a bit like a jumping bean, and then does it the other way. So this is what I meant at the beginning. Okay, so in the context of the aerofoil problem, it's not clear this is especially relevant. It's kind of fun.
Mark, is this motion periodic?
It's not periodic. If you look at the wall carefully, there's a little bit of a wobble. And as far as we can tell, so we didn't look at this very closely, but we computed the Lyapunov exponents for this calculation, and there's some evidence that it's chaotic. It's either chaotic or quasi-periodic. We haven't looked at this really carefully, but it's not periodic. If you look at the time signal of, say, the bending energy of this thing, it's pretty clear it's not periodic.
Yeah, don't aerofoils have a bending moment about the span? So is it related to that?
Bending moment about the span?
But yeah, just an aerofoil, there's a bending moment, isn't there? So is it responding to that? Anyway, if it's not how you think about it.
Okay. Not sure, I'd have to think about that. Here's another calculation. This one, this time, is again, let's show what it looks like. It's very similar to the previous one. You can see the initial state is very similar. Now it's at a larger value of p, and the initial state corresponds to an equilibrium which coexists with a mode 3 equilibrium shape. Okay. Again, there's one unstable eigenvalue from the linear stability calculation, and the unstable eigenfunction looks like a mode 3 shape, which helps to interpret what you see in the movie. Again, it looks static for a while, then it kind of bulges outwards mode 3 type shape, which at the same time is moving downstream slightly, and then this motion continues. But again, although it looks periodic, I don't think this is periodic. I notice it also alternates. The bulging is either at the back or the front. So the summary of that is that there are, at least we've identified two kind of motions here, unsteady behaviours. One is a kind of flipping motion, that's the upper one, and the other one is this kind of intermittent bulging behaviour. Okay, some way removed from an aerofoil, you can see. So let's try and move closer to an aerofoil. Supposing we take the same problem and we introduce into it a corner at the back. So I'm going to put a trailing edge into this thing now. I want to try and force this thing to look more like an aerofoil. Exactly the same problem as before, an oncoming stream, possibly with circulation. I'm going to demand that the angle at the trailing edge is fixed, theta c, and you can imagine that it's possible to manufacture an elastic membrane to do this. So there's the force balance in the absence of flow. Let's start by talking about the solutions when there's no flow. Kind of like analogue of Flaherty's problem, but with a pinch now in the cell. So the other equations aside, I've got to satisfy this integral constraint, which basically says that the angle at the trailing edge is theta c. Okay, and the equation above is the same one from before. P is a constant. Here are some solutions. So these are solutions for fixed transmural pressure and varying the angle theta c. You can see in the middle, the green line, the innermost line, is sort of aerofoil E in shape. If instead we fix the angle, theta c, to be 3 pi over 4 in this case, and I vary p, then this is the effect. When p goes negative, the pressure on the inside is higher than the outside. So it's like you're trying to inflate it. So it wants to go to a circular shape. But it can't go to a circle because it's being pinched at one point. But it does its best. And that's the blue line. So this is less successful in terms of getting an aerofoil shape. It looks more like a dumbbell on the interior state. Here's another pinch angle, just illustrating that you can get self-intersecting shapes, so points with self-contact and then self-intersection. There's some mode 3 type shapes with a pinch and self-intersections like that. The problem we're really interested in is taking one of these states and putting it into a uniform stream with circulation at infinity. Again, starting by thinking about static equilibria. So my kinematic condition is given by that. Wz is the derivative of the velocity potential again. I've got a sharp corner now, so I've got to impose a Kutter condition so that there's a stagnation point at the corner. So little q.
Do you have any angle of attack or anything?
So, well, that's going to be set naturally by the shape, because I don't know the shape at the beginning. Yeah, so that's kind of, I'm going to fix theta c, and the angle of attack is effectively going to come out in the solution. Right, well, there's a nice conformal mapping you can use to do this, called a Karman-Trefftz mapping that I was not aware of before we did this work. This is designed to map a Joukowski, so it's a Joukowski-like mapping, and it takes the unit circle into a Joukowski-like looking shape. Okay, but with a corner at the trailing edge, whose angle theta c is related to the exponent p in the mapping. So p is a number between 0 and 2. It's related to the trailing edge angle like that. Now our problem is that the aerofoil shape, or at least the elastic cell shape we're going to compute, will not exactly be one of these. So there's going to be an intermediary step. So let's imagine this is a solution to my elastic problem. That's not going to correspond exactly to a boundary you get from a Karman-Trefftz mapping from a circle. So what the Karman-Trefftz mapping is going to do for us is take that and map it into a shape with a smooth boundary, with no corner, so it irons out the corner. And then I use another mapping to map that back to the unit circle, and then I can solve my problem in the unit circle plane, the zeta plane, as before. That's the same idea as before, but now we're doing this Karman-Trefftz thing. So here's the setup. There's the conformal mapping from before at the top. That's mapping the smooth, so the second of the three diagrams on the previous slide to the unit circle. And there's the Karman-Trefftz bit with this P exponent related to the trailing edge angle, which we can just take to be whatever we like. And there's a capital A parameter in there, which we have to fix so that the perimeter is what we want it to be. And there's the complex potential in the zeta plane with the circulation included this time. Okay. So here's the problem now in flow, non-dimensionalized, same equation as before, lift, balancing weight, as before. Here's the reminder of what those parameters were. So alpha is the flow speed, roughly, beta is the circulation lift, and P is the transmural pressure. I want to calculate some static shapes. And I want to try and do this so that I get something that looks like an aerofoil. I'll make that a little bit more concrete in a minute, what I mean by looks like an aerofoil. Start being a bit careful about that. The first point to make, so these are solutions now with the Karman-Trefftz mapping. Here theta c is fixed to be, I'm not sure what it is, pi over 6 maybe. The point I want to make with this is that as you increase alpha, the shapes you get kind of balloon outwards. So it doesn't look like an ideal aerofoil shape. As you increase alpha, which is increasing the flow speed, and the colours here incidentally are the speed of the flow, so they're Q. So red is large values of Q. If I increase alpha, this thing just balloons outwards. It doesn't look like an aerofoil at all. And worse than that, it becomes clear that there's a very dark maroon colour at the top and a light blue here. So that's high speed at the top, low speed at the trailing edge. So the pressure is going to be the other way around. There's going to be an adverse pressure gradient on this part of the cell that's going to try to force, it's thinking in terms of a real flow now, it's going to try and force a boundary layer to separate. And everything I'm doing here, incidentally, is assuming potential flow, so separation is not our friend. We don't want that to happen, because then the solutions we're computing are not relevant to a real flow. I'll come back to that point in a minute. Okay, so as you increase alpha, the thing kind of does the opposite of what you want. It starts to balloon outwards. It seems to make aerofoil type shapes difficult to find, but still the pressure difference to play with. The purpose of this slide, so this is again bifurcation diagrams with a pinched corner. This time the dotted lines are the Flaherty solutions for reference, and the solid lines are the solution, the pinched solutions, and the dashed bits are just where they self-intersect. The only reason for showing that is that just to illustrate that bifurcation space is complicated. And if we're looking for aerofoils, there's lots of choices of solution branches to start on before we start increasing alpha. So this slide is all for static alpha. So we choose one of the solution branches and play around with the parameters. And you can see in the top right, there's something that looks a little bit like an aerofoil, but if you tweak the parameters very much, they quickly balloon outwards and change shape so they're not. And if we want something that's actually going to be able to fly under some vaguely general flow conditions, this is not very acceptable. Here's another solution branch from that complicated bifurcation space, illustrating kind of the same point really. But if you can find one shape which looks like an aerofoil, you've only got to play with the parameters a little bit, and it doesn't much anymore. And there's going to be strong adverse pressure gradients on the rearward sides of the upper part of the cell, which will provoke separation. So let's be a bit more clear now about what we mean by an aerofoil, or realistic aerofoil. I want to tune the parameters to achieve that. It doesn't look all that promising so far. And I want to do that so that I get the characteristics of a regular aerofoil. I want to minimize separation. So if there is separation of the boundary layer on the top, I want to push that to the trailing edge as much as possible. I want to have as little drag as possible and as much lift as possible. Okay, well, what we thought of doing next is taking some of these calculations we did under assumption of potential flow and trying to put them into a full Navier-Stokes solver to see what happens, to see how realistic they are and whether or not the boundary layer does separate, whether you get separation, vortex shedding, and so on. But to help us, because obviously DNS calculations are expensive, one calculation you can do before that is to think about whether the boundary layer on the surface of the cell is likely to separate. So here's now we start to introduce viscosity into the talk. Here's the standard boundary layer scalings on a curved surface. So take Navier-Stokes, do the regular boundary layer scalings. RE is the Reynolds number. If you've not seen this before, these are just the standard scalings for the Prandtl boundary layer. And Navier-Stokes reduced down to this parabolic system of equations here. Little q is the slip velocity that we've computed, the potential flow speed on the surface of the cell. And the question is little q as a function of s such that this boundary layer wants to separate? And separation is signified by the vanishing of the skin friction du by dy, or du hat by dy hat, on the boundary on y is not. That's the thing we're interested in. Let's just skip the details of how the calculation is done. So here's a schematic of what I mean. There's a stagnation point at the leading edge or at the front side of the cell. We're going to integrate the boundary layer equations around the shape. So I take one of my static equilibrium shapes, take Q, which is the slip velocity around that from the previous calculations I showed you, solve the boundary layer equations and see if we reach a point of zero shear stress and separation. We certainly expect to do that because of the results I've shown you before. So here's a typical example. The big red crosses indicate where separation occurs. This is the viscous stress, du by dy, plotted against distance from the stagnation point. It hits zero here, which corresponds to that red cross. So that cell is going to separate at the top, and there's going to be a big wake, and that means the potential flow solutions I've been talking about are going to be completely irrelevant to the real flow. So the question is, can we devise an elastic aerofoil and push these red crosses closer to the trailing edge and minimize separation? And the answer is sort of partially yes, as I'll try and illustrate. So this is still now work in progress that I'm going to talk about. You take one of these typical unmanned aerial vehicles, like the one I showed you at the beginning. A typical length scale is about 0.5 metre. Their flight speed, so some of this data is difficult to extract from the literature, and things like the bending modulus of the boundary is very difficult to know what that might be. So we had to make some guesses here. A typical cruising speed is roughly 20 miles an hour for these things. Take the kinematic viscosity of air, we're talking Reynolds numbers something like 10 to the 5. So we took some of our cell shapes and plugged them into a DNS solver. These calculations were done with GERIS, which is a finite volume based solver. Work. So this is a cell with circulation, so beta is non-zero, so there's lift, balancing weight. Alpha is the flow speed, so there's some flow. P is naught, and everything I'm going to show you now has got zero transmural pressure.
Is it capable of resolving with this Reynolds number?
Resolving the boundary layer.
Yeah.
So I think the answer to that is no. This is partly why we did the boundary layer calculations, to try and be careful about this. So this is a calculation at Reynolds numbers 10 to the 5. So there's a starting vortex shed off the trailing edge. The colours here are vorticity, blue and red being opposite signs. And the point to be made here is that there's clearly something near the trailing edge going on. There is some mild separation happening near the trailing edge. And then a wake shed off the back.
Does this calculation allow the airfoil to deform?
That's a good point. No, it doesn't. So I should also be clear about, I was going to say this at the end, I should be clear about this. What we've done is taken a static equilibrium shape and then treated it as a rigid body in a DNS solver. Okay, so it's not correct, but it's the first thing to do. So that's that one. Just done that one. Here's another one at not half the Reynolds number, 5 times 10 to the 4, slightly smaller Reynolds number. This is really to illustrate the fact that if we want this thing to operate at different flow speeds, different Reynolds numbers, you can get dramatically different behaviour. So now the separation is much worse, as you can see. The separation occurring in here is very clear, and you get a much bigger wake and a vortex streak being generated downstream. Okay, so I think the summary of that so far is that these are not ideal as aerofoils. And if we look at the lift, so just look at the purple lines perhaps here. These are the lift generated in the last 2 movies that I just showed you. This one here on the right hand side is the most recent movie we looked at. It's very unsteady, as you'd expect from what we saw. The previous one was better, okay, and the separation looked relatively mild, but the lift coefficient here is asymptoting roughly to something like 1. But the actual lift on the aerofoil that we put into the DNS solver in a potential flow is 2. Okay, so it's some way off that. So it's a strong indicator that that's not a potential flow solution in the DNS. Right, so how do we make this thing look more like an aerofoil? Well, we want it to be as sort of non-intrusive as possible, but we've got to do something, so we thought about putting an internal support in. So what I'm going to do now is put a rigid support, think of as a rigid beam or something, that can't change its length, and it's attached to the cell top and bottom, so it's constraining now somehow how the cell can deform. Fix the angle at the back again, and proceed on that basis. So here are the details of the calculation. All I really want to point out from this slide is that if you look exactly at the jump, where the support is there, how does that affect all the equations that I've shown you up to now? The equation basically set up exactly the same as before. These square brackets indicate the jump as you go across the point where that strut is. Everything is continuous except the first derivative of curvature in arc length, which balances the force imposed by that strut in the normal direction, and this constant of integration sigma that's been floating through the torque, which balances the negative of the tangential component of the force imposed by that strut. Now that means, because those two things are not continuous, it's not obvious anymore how you do this calculation with a conformal magnet. So we took an alternative approach and did it with the boundary integral method. I'll skip all the details of that and just briefly describe how the calculation is done now. So it's exactly the same idea as before. I want to find an equilibrium static shape in a flow with circulation with this strut constraining how the thing can deform. And the way we do it is I want to find Q, right, the certain slip velocity around the surface. If we guess that using some polynomial representation in S, guessing the coefficients of that polynomial, given Q, we then solve for the cell shape, because Q just feeds into the dynamic boundary condition. Then calculate the flow around that cell shape with the boundary integral method instead of a conformal mapping. Then feed that back into the coefficients for Q, and then just keep going round until the thing converges, which it does. Okay, here are some results. So these are for no circulation, because they're up-down symmetric, so beta is naught. And again, what I really want to illustrate here is whether you can get something that looks a bit like an aerofoil. These are for different P, incidentally, these coloured cell shapes. And the ones that look most like aerofoils, the sort of light orange colour, P equals 0, which is probably the most realistic value of P. But starting to look better now, these are looking more like aerofoils. Let's see how they do in the DNS. Again, these are Jeris computations. With cells with struts, now putting circulation back in. Okay, so there's some lift on this thing. It's the same as before. These are treated as rigid bodies in this calculation. Starting vortex goes off the back. The separation looks milder now than before. So the Reynolds number here is, I think, 10 to the 5, within the sort of working operational conditions you'd expect of one of these UAVs. Really, the thing to take from that video is that it just looks better than before. There's not so much separation. We want this thing to look as closely as possible like a potential flow. And finally, so let's do it at a slightly different Reynolds number. Again, the colours indicate vorticity, so we can read this as meaning this is a potential flow everywhere except where the colour is located. And the separation off the back of that is worse, but still this is not as bad as it was before. It's not generating such a massive wake, so there is an improvement. So as I said, this is work in progress, but this was the aim of this, to try and move towards something which you can pack away at the end of the day, but which when you get into operational flight, the question of how you get up to the speed where this works is a good question. Assuming you can do that, then the aerofoil automatically adopts the shape of the aerofoil that you want, and then gives you the operational behaviour that you would like. And just quickly to end up, and so corresponding to those two movies I showed you, is the lift coefficient again for the 10 to the 5 case. It appears to be asymptoting towards a value which is closer to 2 than before, so it's more successful in mimicking a potential flow. And one can play with the length of that strut. It doesn't have to be fixed. We can do calculations with different lengths. And what's happened now is that asymptote has moved up closer to 2 again. Just to briefly summarise what I've talked about, we've described these equilibrium cell shapes and flow with and without circulation, with a view to trying to get something that looks like an aerofoil. To do that, we introduced a pinch at the trailing edge with a fixed angle and some finite support of finite length. And to try and work out how realistic this is, we did DNS calculations, but these are based on taking one of those static equilibrium, treating it as a rigid body, and plugging it into a DNS solver. Whereas in reality, of course, the cell membrane is going to respond to the forces from the flow. So that needs to be addressed, and we need to do a better calculation in future. But I'll end at that point, and thank you very much for listening.
questions for Mark?
Didn't quite understand why you said that you had problems with conformal map in the last case you were talking about.
I think it was because of the discontinuity in the curvature. It wasn't obvious how to do that, because then you've got to think of the boundary as kind of in two segments. So there's the strut, and there's a segment going around like that, which is in some sense independent of this bit. There's a
Have you
discontinuity.
tried mapping to a semicircle, for instance?
Mapping each bit into
So
a
that the different parts going to different places.
Okay.
You could sometimes get rid of problems that way.
Okay. I mean, so maybe I overstated it. I mean, we perhaps gave up a little too quickly. Okay. So also, we wanted to look at. Let's see. So we really wanted to extend the stability calculations as well. Maybe that. Okay. If you could do a conformal mapping, you could do the stability calculation too in the same way as before. Okay. Maybe we should think about that.
You somewhere showed inaccessibility of shell condition. Would you show it again and explain
You mean the
in a couple of
integral
words?
constraint?
Somewhere in the middle of your talk
The
was
integral of
integral from 0 to 2 pi d
Eta by d
eta
phi.
by d phi equals 0.
Yeah.
So what is d eta again?
So eta is just just the cell shape.
I would expect that you would write the whole length of the
Okay,
curve.
why is the absolute
And it should
zero?
be-
You mean it's a constant? That's what you meant?
Oh, that's a good point. Yeah, it can't be 0.
You meant you set that length to
Yeah,
1
yeah,
or something.
yeah.
But would you actually answer to my question?
I'm sorry.
So I would expect that you would write the length of the whole curve that is integral from 0 or whatever to
Yeah.
pi on parametric or physical domain square
Yeah.
root 1 plus derivative squared, and then it's the length of the curve. And it has to be the same as the original one, because
So-
the derivative may be not 0. So what does it mean actually?
Well, so if you do,
I mean, you have a length of the curve that is integral from 0 to x square root 1 plus y prime squared.
yeah, this is equivalent to that. So what you're saying, I think, will assume that it's a graph. Right?
Yeah, but I don't
doesn't-
see the length here. It should be a length.
So that's eta.
Yeah, that's the conformal map, dz dphi, absolute, that's the length element is integrating around. So instead of 0, it's just a constant.
Yeah, I'm sorry. It should be L.
So it should be what?
It should be L, the length of the.
Oh,
dot.
that is what
yeah.
I'm
I
expecting.
know. I'm sorry. That's
Other questions? All right, I've got a question. Doing the DNS with a deformable thing is not a trivial question. Even if these DNSs like Jarvis and Blyth and whatever are fairly easy to use from the outside, they don't deal very well. You have to set up a whole parallel set of
Yeah.
equations.
So Jarvis won't easily do this with an elastic mapping.
I have very few codes will.
Yeah, so it's, I agree, it's highly non-trivial. So I'm not saying we're going to do it. I think it needs to be.
Good, someone needs to do it. Any more questions? Okay, let's thank Mark again. Thanks a lot. And just to point out that we